Hi there, welcome back to the channel. Welcome to the next installment in the Back to Basics series on tube radio restorations. In this video I'm tackling the power stage, the power output stage, and by the end of the video we'll actually be able to feed a signal in and see the result. See whether we have the power supply working and the audio power amp working as well. In the meantime, or before we get there, we'll check how the tone controls, the basic tone controls like treble and bass, how they work. We'll see how they are implemented in this radio, and at the end we'll be able to check their effects on with an actual signal coming in and going out through the speakers. So if this sort of thing interests you, stick around and enjoy the video. When I left off last, I said I wasn't going to power it up because there was still something I wanted to check on this output stage. Let me show you what it is, but first of all, let me put some of these hidden elements back. These are the hidden parts of the schematic that I'd hidden away because they didn't relate specifically or directly to the output stage. But there was something here that does, okay? And it's got to do with this over here and the way that the electrostatic tweeters are actually powered and given a signal to reproduce. So let's have a look at this a little bit more closely. If I put the component values on here, this is what I get. I've actually got a connection between this point and the electrostatic tweeters. You can see that there are two ways that voltage can get to electrostatic tweeters. Now, why is this? Well, the way electrostatic tweeters work is really interesting. I would definitely recommend you do some more research on that, because the way they set it up is that one side of the tweeter is connected to ground, and there's an insulating plate between it and the other end of the tweeter, or the other element. And that side is supplied with a high voltage. So you're left with two plates insulated from each other with a high voltage between them. And then what happens is that when a signal is superimposed on that DC charging voltage through this capacitor C182, that's when you get those tweeters or those elements vibrating between each other and creating the sound. Of course, you only want high frequencies to go through, so how do you stop the low frequencies going through? Well, you put a capacitor in place, and you put a fairly small capacitor that's 2000 picofarads, so the majority of the audio is being induced through here. The driving stage driving the primary of the output transformer, which then goes to the speakers. But you want those high frequencies only to get through to the electrostatic tweeter, and the high frequencies will be allowed through while the low frequencies will not, because this is a very small capacitor. Remember, a capacitor likes to let high frequencies through. The bigger the capacitor, the greater the shift down the frequency range those high frequencies become. So if you had a 100 nanofarad capacitor here, you'd probably get the entire audio range trying to get through. This would not be able to reproduce that because this is only made to reproduce high frequencies. So you throttle out the low frequencies with this capacitor and you feed it to this electrostatic tweeter setup, which has been pre-charged by the B2+. See that? B2+ down here goes up there, goes up there. Now there are two ways it gets through. The simplest way is through this line here where these two switches are closed. We'll see in a minute how that works. If these two switches are closed, it means that gets through, that gets through, that gets through. It gets to here. It meets a 33K resistor and it charges the plates. It keeps them at a high voltage. All right. The other way that it can get through is through this resistor here. But this resistor here is made redundant when those two switches are closed. So these two switches basically take that resistor out of circuit. Now let's check first of all if these lines are there. If the resistors are fine, I definitely will be changing that capacitor, and we'll see why this is set up this way. This is the point where the electrostatic tweeters are connected to. And if you recall, I cut the wire off, but I left a little bit of wire so that I knew where it was. So I'm going to connect one side of the multimeter to that. And if we look at the schematic, we see that I'm going to try and measure from pin 9 of the EL84 through here, through there, or through there to the electrostatic tweeters. So let's see what I get if I probe pin 9. I get 48K. Is that correct? Let's have a look at what we expect. 48K means that I'm getting that resistor in series with that resistor. 48K should be 51, 48 is close enough, which means that one or both of these two are open But when do these guys get activated and why? If I go and probe pin 9 again, I just happen to have it on FM and I'm getting 48. If I put it on medium wave or short wave, I get 30. You see, now I'm only measuring that one resistor. Now the switches are bypassed. Now that 18K resistor is bypassed. So medium wave bypassed, pickup bypassed. So FM, it's open. I'm trying shortwave, medium wave, pickup, and bass. See, now the bass opens it up as well. So we know a few things. We know that FM opens that up, and we know that bass opens that up, because when we select FM and or bass, so it could be both or one, that circuit opens up. So it allows this resistor to come into the circuit. But we know that this is now fine, and we've just got to figure out why this is the case. So we now have that checked. We know it's working, but why is it working? Why is it done like that? Well, let's try and figure this out. When we have FM and bass not activated, then we are getting these guys closed, and we are getting 33K to ground. So what is happening here? Well, I've got to figure it out as I speak to you. Maybe I'm going to get this wrong, and perhaps you can correct me. Let's start with bass. When I select bass, this resistor comes into play, which means that fewer high-frequency sounds come through. So the voltage that's going to get there, the charge that's going to get there, instead of the voltage going through a 33K resistor, it's now going through a 48K resistor, which means that these are going to be less active. So these are going to be less active when I select bass, which means that more bass sounds come through. That makes sense, right? That does make sense. The same feed is going through there. That capacitor stays the same. But if the charge on these tweeters is lower, then you're going to get more bass because we're going to get less treble. Yeah, that seems to make sense. Same applies when you hit FM. When you hit FM, why do you want less treble? Well, when you're listening to AM bands, the AM bands are actually more speech than bass, okay? So you want more speech, which means that I'm just trying to think of something here. If you have FM selected, but you don't have bass selected, it doesn't make any difference. So my argument is actually falling flat. It means that when I have bass selected, the bass only increases if FM is not selected. I tell you what, I can't figure out why they would do that. I can see how they do that, because if I have bass selected, this is open, then it doesn't matter what I do with FM. It doesn't matter whether it's AM, pickup, it doesn't matter. The treble is reduced. So effectively what they're doing here is they're making sure that if you want bass selected, you're only going to get it if you have it on FM. Probably because the quality of the sound will be good enough, otherwise it'll just be very muddy and boomy. Might make sense. Anyway, those lines are checked. I'm going to remove this capacitor, replace it with a 2.2 nanofarad. You can't really get 2 nanofarads. You can use 1 nanofarad in parallel, but it's not that critical. 2.2 is fine. I'm going to remove it. That's that capacitor there, and those guys are notoriously bad. I don't think I've ever seen one that's good. So what I'm going to do is remove it from the underside. It's not a big deal, and replace it. And then I think we might be ready to just power this up without the preamp tube, because what I want to do is I can feed the signal to where it should be coming out of the preamp tube. So I can feed it to the start of that capacitor, feed a signal, and we should get it out of the speakers. Let's do that. So I've now replaced that capacitor. Here it is here. What value do we get on this thing? 4.5. 4.9. This is supposed to be 2, so it's 2.5 times higher. So replacing that was a good move. And that means we can now complete this here. And we've gone one step further in the circuit. Good. Now what can we do here? Well, we've effectively completed this section. I'm not connecting the electrostatic tweeters when I tested. That's really done at the end. But if we go back, there are a few things we'd skipped on here. I just want to see what it is that could affect this triode from working, or from, yeah, I'm going to focus just quickly on this here because what I want to do is I want to feed a signal here, which means it should go through there. I'm going to have to short out those two because we don't have this part connected to the radio. So I'll have to short out pins 6 and 7. But if I feed a signal to here, it'll go through there, which we've replaced already, into there, through there, and we should get it coming out of the speakers if we connect a test speaker to our radio. What else do we have on here? I think I'm just going to complete this description here so that we don't take any chances and we can actually be sure that the entire signal chain from here to there without the tube in is completely safe. You know, I've been talking about tone shaping and I've been using the analogy of the hose pipe and all sorts of stuff, but there's no better way to do this than to actually see the results. And the first example is this guy over here. What we have is the audio signal coming through. It's getting out of there and it's coming through here. And then we've got this thing over here, this situation with a capacitor and a variable resistor in parallel. And I think just previously when I described how this worked was you allowing more or less of the bass to go through compared to the treble, which goes through the capacitor. Now, the easiest way to do this is to actually show it, do a little bit of a test on something like LTSpice, which I actually quite enjoy using. So I've reproduced a version of that schematic. Basically what I've done is I've created a signal source over here. It's producing a sine wave, 1 volt peak to peak, I think it is. And I've got it going through this same system that we have on the schematic. So I've got a 300 picofarad capacitor and I've got a resistor in parallel, and I've made that resistor variable in steps, starting at very low. In this case, I've started at 1K. I've gone to 10 meg, which is 10,000 K, and I've done it in 1,000 K steps. So I'm going to create sort of 10 steps where the first one will be 1K, the second one will be 1 meg, then 2 meg, then 3 meg, and so on. So basically simulating changing the position of that variable resistor over here, and it is meeting the same 680K resistor that we have there, as well as the 100K resistor going to the grid. Now, this doesn't really need to be drawn like this, and this is by no means exact because we don't really know what the input impedance is that we should put over here. I know it's supposed to be high, but how high, can't tell you. I also, without going to a lot of research and calculations, can't tell you what the output impedance of this source is. Now this will be the tube, the triode, but it'll give us a fairly good indication of what's happening to the shaping of the frequency band as it goes through this with the various steps. Let's try that. Let's simulate, and we're going to look for the signal here. We can do it here or here, and this is what we get, which is a fairly good indication, by no means exact, and I don't mean it to be, but here's the indication that we've got. We've really got this green line over here is when our pot is set at 0. It's actually set at 1K because it won't allow 0, but let's say it's set at 0. And it's letting all the frequencies through, all the way from, and I've started here at 20 hertz, there's 100 hertz, this is logarithmic, there's 1 kilohertz, there's 10 kilohertz, and that's 20 or 30, 20 kilohertz I think it is, 20 hertz to 50 kilohertz, okay. So we're looking at 20 kilohertz is over here. And look what it does. It allows all the frequencies through. The minute you put that pot up to 1 meg, you get this blue line. And this blue line starts showing us that the lower frequencies are actually attenuated. They're not a constant attenuation. It creates a shelf. Okay, if you look at this as a shelf, and then it starts going up, and it goes to the next shelf or plateau. So you are getting a certain amount of bass going through, but it's certainly less than it was over there. It's showing us 2 dB for every tick. There's minus 2 dB, so minus 3 dB is over here. So in this blue line, our minus 3 dB point is at 1 kilohertz. Now, this is actually quite high. Probably in real life would probably happen a bit lower down. Remember, I have not got all the input and output impedances correct here, but it does give you an idea. So the more you increase your potentiometer, your variable resistor value, in other words,
as you turn your bass clockwise, what's actually happening is that your bass frequencies are getting lower. You see that? That's a 2 meg. That's 3 meg. That's 4 meg. That's 5 meg. So when you're down here, you're turning clockwise and your bass is being cut off progressively more. This is strange with these radios that the bass control actually seems to work in reverse. When you go left, in other words, when you go counterclockwise, you get more bass. When you go clockwise, you get less bass because it cuts off the bass frequencies. And as you can see, the treble frequencies, or the frequencies above a certain point, are generally the same because the capacitor starts taking over and it's passing all the higher frequencies through. So I hope that gives you an indication of how that little part works. That being that pot over there, which is our bass pot, okay? Now we can go one step further because we are trying to follow this back through this section. We've actually got this over here, which we'll see later, but it's exactly the same thing, you see. We've got the same situation here that we really had here, except here it's done for a different reason. You've got this capacitor here, this 300 picofarads, and if you have this in place, it's as if the capacitor does not exist because that line is just shorted through. But when you remove that, then your capacitor comes in place, comes in line, and that's because you've pressed speech. And if you've pressed speech, that thing opens so that all the signals from here have to pass through that 300 picofarad capacitor. And what it's going to do is really a fairly drastic version of what we saw with this one. You are going to effectively force the frequencies to go through a very small capacitor. So your bass notes disappear. You don't have a gentle curve because you don't have a variable pot. They just disappear. So we can also go back here and you've got a different situation here. Now this is actually the treble pot. And the way this works is actually interesting as well because I like to look at this as a treble bleed. And the reason I say bleed is you've got all your frequencies here and it meets a capacitor. If this was connected to ground, the high frequencies, all those that love capacitors, would just escape to ground. They just shoot off to ground. They would not go through to be amplified. However, you can say, whoa, wait a minute, we can control how much of that will go through. So you can set this variable resistor to create a bigger or a smaller blockage to those escaping high frequencies, which means that you have control of your treble. And we can reproduce that as well in our LTSpice model. And here I've reproduced basically that circuit. Again, we've got the signal source, we've got that going off to the input, and we've got actually, what do they say, 5,000 picofarad. It's a 5,000 picofarad capacitor in there. And there is the pot is a 1 meg pot, according to the schematic. So let's simulate this and see what we get. And here we have the result. Now, forget about where this is happening on the frequency, because this should be way up here. I haven't considered the pre and post impedances, but you can see the result here. When you have, when you've set it to the highest level, you've got this result over here. You've got very little treble bleed. So that means that your treble goes through. So in this case, it works in the opposite way to the bass. The more clockwise you go, the higher the resistance, the more treble you will get, because less and less of your high frequencies are escaping to ground. Now, it creates a shelf, as you can see. It doesn't sort of continue down. It's not a filter where you get so many dB per octave. It actually goes down and then it straightens out again. And you can see the result as you decrease the potentiometer, the resistance. Here's the case where you've got very little resistance and all the frequencies find a way to ground because it's basically shorted to ground. All those the band is seeing is a capacitor shorted to ground. And as you increase that resistance, it goes up, 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 and less and less and less treble escapes, which means that your tone, your sound, becomes more and more and more treble rich. I hope that's explained it. Let's just continue with our checking. Here we go again. We've got the treble pot, which is this guy down here. And we know that one side is connected to ground, so I'll just check which one it is. I think it's that guy. Yes, it is. And then we know that that one is supposed to be 1 meg. Not bad. minimum, doesn't go quite to ground, so 133 ohms, and the top is at just over 1 meg. Okay, good. So I'm going to put this at minimum because I know that this leg, the yellow one, that one there, should go to a capacitor, to that 5 nanofarad, 5000 picofarad capacitor. That would be capacitor 145. So let's turn this around and see what we get. I believe that we're talking about this capacitor here, so let's just check. I'm going to go to that point there to ground, and I'm getting 130 ohms, that's the one. And I know that this side should be going to pin 9. It's in really bad shape, that yeah, I'm checking, that's it. So that's the capacitor I have to remove and replace. I'm going to replace it with a 4.7 nanofarad capacitor. This one is really just breaking apart. And the reason for that is that this capacitor is always under high voltage. You see, that voltage there would be fairly high voltage, 55 volts. It's not just an audio signal, it's actually got a B+ supply coming through here. So this one is always sort of under stress, and those tend to show their age, and they tend to break apart and bubble and everything else, which is what we're seeing on this in this case here. So let me remove that and we'll carry on. Right, this is where we got so far. I replaced that capacitor as I said I would. That was capacitor 145. I replaced it with 4.7 nanofarads. The original was 5000 picofarads, close enough. Then that one there is that 100 picofarad capacitor we see going down from pin 9. That one over there. Now that capacitor is also in very poor shape. That one there is 100 nanofarad, which I've also replaced with that guy over there. So I have replaced everything I need to replace here. I've checked these resistors, 220, 220, they're perfectly fine. Those are perfectly fine. All those resistors are fine. So it looks like we've got just about everything beyond the anode done. And what are these components that I've replaced? That one there is simply another filtering stage to create what I suppose you could call B3+, because it comes from the B2+ over here. And remember, to get B2+, we went from B1 through a resistor to a capacitor, a pi filter. And here we've got the same thing, resistor to a capacitor, pi filter. Now the amount of current this thing draws is very small, so you don't need a big capacitor here. Sometimes you would have something like a 8 microfarads or 10 microfarads, but they just put this here, which creates another level of filtering. This is another pi filter to give you a really clean supply here, and also to remove any RF from this line, from going back up through the into the power supply. Remember, filtering works both ways. You can filter from there to there, but you can also filter from this side to that side. And so here we've got another resistor of 220K, and then this is 100 picofarad, which really is just a really high frequency cleaning element. It shorts any RF that is on this tube to ground, so it doesn't go through to the audio stage. Because this tube is doing multiple jobs, and two of them at least, the detection and the modulation, are RF. There is RF working around this tube, so some of it could leak to the triode, and hence you've got that filter over there. So effectively what we've done is we've finished this stuff here. And so we get this. All this has been checked. I need to short between 6 and 7 when I test this stage. And let me show you what these components look like. Here are the 3 capacitors that I've replaced. These guys I'm not even going to check because I don't know if you can see it, but it's all hollowed out. The wax has sort of come off. It's just breaking apart. This obviously got hit with high voltage and it just couldn't take it. This one is different. This one was replaced. This is a new or fairly new capacitor. And the reason I know is it's a different type. It's a film type, and it wasn't actually soldered through the board. They cut the old leads and just tacked this one at the top. So what are we getting here? This is probably not going to be too far off. 120 instead of 100. So not too bad, but it also goes into the pile of bodies over there. And this section is all done. Getting everything ready to switch on for the first time is something you've got to take a bit of care with. The first thing I do is I clean the sockets of the tube, and I use this
These are those dental devices to clean between your teeth. Put a bit of contact cleaner and just go up and down on all the sockets. Get them nice and clean. I've done this already. Of course, cleaning the tube pins is just as important. So what I do is I get a wire brush and just brush away. Try and get both the outside and the inside. I've done this already. I'm just showing you how I do that. And now we should have this perfectly cleaned up. The socket's in perfect condition to receive the tube. And we can put the tube in. And it looks like we're good to go. Now, where are we going to feed the signal into? Well, there are various points where I can actually feed the signal into, and each one may have a few issues that one has to take care of. If we look at the schematic, what we're looking at here is we want to feed the signal into here. You could actually feed it straight into there, but that's not something I normally do. So if you go back, you can feed it into here. So you can feed it into the, that one of the wires in the tone control and the bass control. But we can actually go back further. We can feed it into pin 7. Now pin 7 is over here. If we're looking at it counterclockwise, so 1, 2, 3, 4, 5, 6, 7. We know this is a 9-pin socket, so that makes sense. 9, 8, 7. We can feed it into pin 7. And if we do feed it into pin 7, we will have control of the bass. The bass will come into effect here. But we can actually go back and we can short out between 6 and 7. We can actually fit a little short in there, and I'm going to do that. Now this is all being done with the power off. You've got to be very, very careful. You do not have power on at this stage. Some of these places have got high voltage, and the best way to avoid getting surprised by it is not have it on at all. So I've shorted out pins 6 and 7. We can double check. That's 9, 8, 7 shorted to 6. That's fine. So I guess I could just feed the signal into that lead, that short, but I can go back further because I want access to this treble control. So I'd like to feed it into pin 9 of this tube, meaning that guy over there. Now what I could do is take the signal generator lead, connect it to a ground, and put it into pin 9. But I can't do that. I can't do that. I'll tell you why. Pin 9 is connected to the B2 plus over here, and it tells us that it's 55 volts. Well, I got to tell you, it's not 55 volts. It's going to be much, much higher because there is absolutely no current draw on here. This tube does not exist. This is a blocking capacitor. This is a DC blocking capacitor. That's a DC blocking capacitor. Those two capacitors prevent any DC current from flowing through, which means that there's zero current through 440k of resistance here, which means that this voltage here is the same as that voltage there, and that voltage there is probably around 200 and something, close to 300 volts. In these conditions, because we've only got one tube that we're going to put in, there's nothing else really drawing any current, so the B plus is going through, creating B2 plus, very close to B plus, and then you are getting that full B2 plus over here. So you've got to be very careful, and that's why you need to use a DC blocking. So I use this capacitor. This is a film cap. I've used 47 nanofarads. I think it's probably more than enough, into pin 9. And I can now connect signal generator to that. So it's not going to blow up my signal generator input, or output in this case. Therefore, in summary, I'm going to be feeding the signal into here. I'm going to feed an audio tone like 1 kilohertz or 800 hertz into here. I'm going to start with about 1 volt RMS. I'm not sure how much I need here to get this thing to full deviation, to clip. I'm going to connect the speaker leads or speaker output to my workshop speaker. It's going to go into my dummy load or load controller, which means I can see this on the scope, which is very useful. And that's about it, but I just want to show you how I power this on. What I use to protect myself and the equipment in the event that there's something catastrophic in here. First of all, I don't connect it straight to the mains. I connect it to my dim bulb limiter. I could use the Variac to start at a lower voltage, but I'm not going to do that. I'm just checking that this is 230 volts. So I'm going to put all the lights off except one. So I've only got a 40 watt bulb in here. Now that's a very, very tight restriction. If there's a short on the radio, the maximum current that will allow through will be the current that a 40 watt bulb requires to light up. So it is as safe as it can be. As we get going, I can increase the amount of power that I'll allow through. This is a 40 watt bulb. I can add a 60 watt bulb in parallel, which means I've got the same as having a 100 watt bulb. I can go further all the way, add them all, and I'll end up with 200 watts, but I'm starting off with that. I've got it on limit, and all I'm going to do when I power it on is switch that guy on, because I'm going to leave the radio ready to receive power. And of course, to do that, I've got to select one of these. It doesn't matter which one I select, because at the moment I'm not worried about the preamp, but I do need power to the radio. If I don't have any of them, no power will come in, so let's leave it on pickup. I'll set the signal generator to 1 kilohertz. Now let's leave it at 800 hertz. Amplitude 1 volts RMS. I'm actually going to drop that because I don't know what I need. So I'm going to get 0.5 volt RMS. I'm not sure how much I need, so I can always put it up if I need more amplitude. I can put that on now. That signal is going into there through the DC blocking capacitor, coupling capacitor, so it's going to stop DC from coming back to the signal generator. That's very, very important. Now remember, it doesn't matter what volume level I have here because I've got no volume control. My volume control at this stage, because it's not going through the preamp tube, is simply the level that I send from the signal generator. So I do have to be careful. I've got the speaker on. There's my speaker connection going to the one side, one speaker input of the dummy load controller. I've got it on speaker. It's down. Okay, I've got that output being monitored by the scope, so we'll be able to see that. I'm doing a screen capture of that as well. So I think we're just about ready. Now the important thing to watch here is that light bulb, because when I switch this on, it means the radio is going to draw power. It's only got one tube, so it shouldn't draw that much current, although it is the power tube. It'll draw the most of all the tubes. But I want to make sure this thing, it'll glow, it'll pop up, it'll light up, and then as the capacitors charge, it should dim. And then as the power tube warms up and starts drawing current, it should light up a little bit more, but it shouldn't be absolutely bright, okay? Now, be careful. This is supposed to be a sort of a teaching video, so I'm going to tell you, if you're playing with this, you're doing so at your own risk. Be very, very careful. High voltage can kill you, so let's hit it. See that? It sort of flashed and then it went down. Now, I'm listening for the audio on the speaker because I do have the signal going in and I'm not sure that it's going to come. Ha, there we go. Okay, that is loud. Let me bring it down a bit more. I'm dropping the amplitude on the signal generator. You can see that it's sort of a dull glow. It means that it's drawing current. It's drawing 100 milliamps. And because it's drawing current through the light bulb, the radio is only seeing 191 volts. So everything should be safe. So let's go back to the radio and the scope and see what it is that we're actually seeing here. There really isn't that much to see. All we're seeing on the scope is the signal. Now, if I increase the amplitude from the signal generator, you can see it go up and up and up. And I'm going to put this on dummy load so we don't have to listen to it. I'll give it 8 ohms. We can still see it on the scope, so everything's good so far. But I do want to show you the voltages we're dealing with here. Let's see if I can show you this. This is the pin 9, where we're feeding the signal into 236 volts. See that? Because that tube is not dropping any voltage, it is seeing almost the full B+. It's seeing B2+. That's why you've got to be careful. There is high voltage on here. The actual interconnect pin over here shouldn't have any voltage, and it doesn't really because it's DC blocked with all those capacitors. But let's see what we can do here. What is it that we can actually sort of see? We're seeing our signal, 1 kilohertz, or it's 800 hertz, and I'm going to increase the amplitude on the signal generator. It's a 300 millivolts RMS. I'm going to give it 1 volt. There's 1 volt. And what we're seeing on the output using an 8 ohm load, dummy load, is 2.2 volts RMS. Let me go up further. I want to see when this thing starts to clip, and it's starting there, you see? You see the top of the waveform starting to get flattened, which means we've sort of reached the peak there. Now, if I leave it there where it's sort of flattened, and I give it one more light bulb, Remember that guy over there? I'm giving it one more light bulb. It means that our voltage is actually going to increase. I think I can actually give it some more. I'll give it another one. It means that our voltage increases, and it should be okay. Let me take it down a bit. That is 3.8 volts. I suppose if you want to call it, if you want to get a perfect sine wave, I suppose it's something like that, 3.26 volts. That's more or less what it is. But that means that we've got very little power. But I can assure you, if I put this thing on speaker, it'll blow us out of the water. 3.6 volts or 3.3 volts is about 10 divided by 8. So V power is V squared over R. So we've got V squared is 9, 10 divided by 8, 1 point something watts. It always surprises me how little power you actually can measure on this and how loud it actually is. Because believe me, this thing is loud. Let me go down to 1 volt again, because I want to see what effect we have, or the bass controls will have. Now we're at 800 Hertz. I'm going to drop the frequency down to about 200 Hertz. And I want to see what the effect of the bass control will be. So here's our bass control. And it is on the left, so it's on maximum bass. And here we go right, and it drops quite a bit. You see, our bass control works perfectly well because the bass control actually has the effect on the signal going to the speakers and not the ones going to the electrostatic tweeter. If we try here on the treble, now I'm going to give it a higher frequency. I'm going to give it like 4 kilohertz. Adjust the scope. Now, if I play with treble, I get very little effect. And the reason is that 4 kilohertz is really being controlled or being produced by the electrostatic tweeter, not by the main speaker, which is what we're monitoring now. If I had the electrostatic tweeters on, I should see the effect. But because this is on the main speaker, we don't see that much effect. If I drop this a bit more, let's try 2 kilohertz. This might have an effect on it. It sort of has some effect. Let's try lower. Adjust the scope again. Yeah, you see, the lower you come down, in other words, when you come down to the range that's primarily produced by the main speakers, you see the effect. There is one thing we can do, which is to actually monitor the electrostatic tweeter output. I'm not sure if we'll see this too well without a load on it, but we can certainly try. Because if I put on channel 1, now I need to give it a lot of, it's going to be a 10-to-1 probe. Channel 1, 10-to-1 probe. Because I'm going to be measuring something like 200 volts. Okay, the probe's on 10-to-1. I've got, is this AC coupled? No, AC coupled. And now I'm going to probe. Actually, just to prove what a coward I am, I'm going to go through a DC blocking capacitor as well before the probe. So let us see. Connect this to ground, anywhere will do. And now I'm going to touch it to where the electrostatic tweeter comes out. There's no load on there, so it's acting very funny. But what I want to do is I want to see what happens if I push bass. You see? I've just pushed the bass control. Remember, the bass puts it in, or takes, yeah, let me try. FM, the minute I go to AM, it's gone. Bass, it's there. FM, it's there. So it was actually the other way around. Our electrostatic tweeter, there it does have some effect. Bass, and then it's gone. Okay. Well, that certainly showed me how wrong I can be. In other words, the electrostatic tweeter gets a signal
when either bass or FM is connected. What happens if I put both? You can't really, can you? But if I put the others, there's nothing on the tweeter, so that switches off. This doesn't really make sense to me, so if you can figure it out, make a comment below. I seem to recall that there was the UKW, the FM and the bass control were in series, so it had to be both, which means one is off, one is on. It's probably reversed. If you can figure it out, let me know. The point is, there it is, and we're on 4 kilohertz. Let's go higher. Whoa. 20 kilohertz, that is high. And then it starts going down. So this output is starting at, we go down, I'm going down in frequency, and I'm at 1 kilohertz. It sort of starts, and then it starts picking up from 1 kilohertz onwards, going up in amplitude, and then it starts coming down at about 20 something kilohertz. Now obviously I don't think I'm not sure what range those tweeters have, but I'm sure that's far too high. It's certainly too high for our needs. My ears can't get that far. So what you're seeing there is a 4 kilohertz signal from the electrostatic tweeters, which is adjusted by the treble. Not that much effect, the treble. I think it might have to do with the fact that the output is not being fed by the tube itself. You know, the preamp tube, I'm actually just feeding it direct in there. So output impedances and everything else have to do with it. I'm sure that's what's having an effect on there. The point is, we now know that our power supply is working. So the filter capacitor replacement, the selenium rectifier replacement, all that is working. The repairs or the changes we made on the output section is working. Our output power is working. and we don't know about anything else. And we don't really care, because if either of those were not working, in other words, if the power supply wasn't working and if the power output stage was not working, we would get nothing from this. As it is, we're getting a nice sine wave. We're getting a tone. We have a very simplified power amplifier on here. And it's if you put music through here, you can feed music through there. You've got yourself a mono tube power amplifier. Whoopee. Right, folks, this is where I'm going to leave you for now. And the next time when I come back, I'm going to hopefully have the entire preamp switching section, tone shaping section, all that explanation ready to give you and to put you to sleep for another half an hour or so. So I want to thank you for your company. Hope you've enjoyed that. And if you have, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon and PayPal. Links are in the description below and at the end of the video. Once again, thanks for watching. Bye for now. And most of all, stay safe.